reviewing some aspects of the D0, D4 quantum mechanics, which can also be viewed as a kind of UV description for the quantum mechanical system on the instanton moduli space of 5-dimensional maximal super-Young mirrors. After briefly recalling that, I'll try to explain to you the index of this D0, D4 quantum mechanics in Coulomb phase, which actually is the famous Nekrasov partition function, which he calculated in 2002 with the motivation to study the Seiberg-Witten theory in a microscopic way. Okay. And then in the remaining time, I'll be discussing various physics that you can extract out of it. First of all, to understand the Coulomb phase physics of the 6-dimensional theory, compactified on R4 times T2. I mean, with the help of the instanton-Kaluza-Klein modes. And then as a little bit of precursor for the usage of this kind of objects in conformal, in the superconformal 6-dimensional theories in the unbroken conformal phase, I'll try to explain to you how you can use this Coulomb phase partition function of Nekrasov to understand some conformal phase physics of the 6-dimensional theory in the DLCQ setting. Okay, it will be a much more simplified version than the more elaborate observables that I'll explain to you tomorrow. So let me just briefly recall. This is basically what I explained to you in yesterday's lecture. The quantum mechanics of TQD0, KD0 brains, marginally bound to ND4 brains, is described in a certain limit that I explained to you by the following quantum mechanical system, where there are 5 scalars which are taking the form of K by K matrix values, which probes a 5 transverse direction to the D4 brains. And there are 4 adjoint scalars, again in K by K matrix, which are the D0 brains positioned longitudinal to the D4 brains. And there are extra K by N matrices which are labeling the light D0, D4 string degrees of freedom. And there are lots of potential terms governed by, which is basically given by the Yang-Mills quantum mechanics and so on. And the possible deformation that you can insert to see various physics is firstly you can put the D4 brains in separations. I mean, putting the 5-dimensional Yang-Mills or 6-dimensional CFT in the Coulomb phase. In the Coulomb phase, you see that the Coulomb wave for the bulk scalars of the 5-dimensional scalars induce some extra potentials on the D0, D4 light strings, which will be important for some purpose in the calculation. And secondly, I explained to you in yesterday's talk that the instanton moduli space quantum mechanics dynamics has some small instanton singularities, so that you have to give some UV prescription beyond the 5-dimensional Yang-Mills to get an unambiguous physics. So for this purpose, you can deform the UV theory a little bit, and the useful thing to do is to deform this quantum mechanical system by some F-Lioploston parameters, which amounts to turning on some constant Mouvet-Schwarz B field on the world volume of the D4 brains. Okay, so yeah. Oh, these also, yeah. Oh, so yeah, I'll try to explain to you now. Do I have a slide later? I'll just explain now. Okay. Maybe there will be a slide which explains all the symmetries, but I'll try to explain to you now. So I'm just the problem is just trying to understand the spectrum of the massive particles in 5 dimensions. So the Lorentz symmetry effectively breaks down to this little group SO4 on the spatial slice, which can be decomposed again into the left SU2 and right SU2. And since there will be many SU2s from space-time and internal part, let me call this first SU2 left and first SU2 right. Alpha, I'm not having alpha indices here, but there are some alpha indices for fermions. But undotted alpha are for these left-handed fermions. Dotted alphas are for these right-handed fermions. So these all assume 1 and 2 indices. So these are, no. Q is a bosonic variable. And each one is K by N matrix. So these are the scalar modes which correspond to the D0, D4 strings. Yeah, one by fundamental. Well, Well, if you view it as a reduction of let's say 4-dimensional or 6-dimensional Yang-Mills theory with 8 supercharges, this just corresponds to hypermultiplet, and which is in this hypermultiplet scalars are doublet under this SU2R symmetry. So you can view it in that way. Yeah. And also these 4 scalars can be traded into bispinors this way. Okay. And also I may have to explain the R symmetry, which will also appear. So by putting the system in the Coulomb phase, let's say by giving the 5th scalar non-zero expectation value, which I will do which is what actually Nekrasov does in his calculation, the SO4 R symmetry is broken down to SO4, okay, which can again be decomposed into the two SU2 left, SU2R. Okay, let me call this second SU2 left, second SU2 right. Okay, I label this by undotted A and dotted A, which again runs from 1 to 2. Okay. Any other questions about notations if it's confusing? Sorry, well, I should have prepared all this explanation here, but you know, this system is full of stupid indices, so it's just, yeah.
But as you say, it's very clear. It's basically by fundamentals,
yes.
And the AMs are the gauge fields of the 4, are the longitudinal motion of the
yes. You have the world line gauge field, which is all hidden in this time covariant derivative. Yes. Good. It can be obtained as a dimensional reduction of, let's say, some higher dimensional super Yang-Mills, quantum mechanics. Okay. So, as I told you before, this system has some unwanted degrees of freedom if you're interested in studying the 6-dimensional physics. Namely, it has some D0 brane degrees which are unbound to D4s. And I call this the Coulomb phase degrees, Coulomb branch degrees, contrary to the D0, the 6-dimensional degrees, which I call the Higgs branch degrees. Okay. So these Coulomb branch degrees roughly correspond to these 5 scalars, which tend to escape out of the D4s. So I told you in the previous talk that, taking a special limit of this system amounts to decoupling these Higgs branch unwanted degrees from the 6-dimensional degrees of your interest. So for instance, if you take this quantum mechanical gauge coupling to be very large, in the Higgs branch, the Coulomb branch fields turn out to carry very, very large mass proportional to this, so they effectively decouple. So in the strong coupling limit, you are getting a decoupled 6-dimensional system that you're interested in. Or either, or in other ways, the Fi parameter, which is a UV deformation of the theory to study the small instant of physics, is always playing some similar roles. Because if there's some Fi terms in the D-term potential, the hypermultiplet scalars are always required to be non-zero. That's the characteristic effect of the non-zero Fi term. And then, and with non-zero Fi term, it plays the role of actually separating the Coulomb and Higgs branches. And the Coulomb branch scalars fields always carries a mass square proportional to this. Okay? So if you calculate some index after using this kind of deformation, Coulomb branch fields are always dropping out of the calculation, and you're guaranteed to study the Higgs branch or 6-dimensional physics you're interested in. So this is the kind of technical deformation to make the calculations unambiguous. So in this kind of system, from the 5-dimensional or 6-dimensional perspective, the particles that you're going to study are the following. So from the 5-dimensional perspective, I don't have enough space, so I draw the D4 branes by a line. But just imagine this is a 4 + 1-dimensional world volume. So you separate the D4 branes, and you can have some W bosons, which are nothing but the fundamental strings suspended. And it can be bound to D0 branes as well. So you're counting the bound state degeneracies of these objects. In the M theory, in which you have the extra circle direction, or M5 branes, the fundamental strings will uplift to some self-dual strings of M2 branes, wrapping the circle direction, and the D0 brane will be just a worldsheet momentum. D0 branes bound to the fundamental strings will just be the worldsheet momentum of them. So you're studying this kind of systems from 5D Yang-Mills viewpoint. Each of the constituents turn out to carry half supersymmetries. So if you decompose the 16 supersymmetries of maximal super Yang-Mills, it carries 8 supercharges which are chiral in this sense and antichiral in this sense. Self-dual instantons are preserving half supersymmetries which are antichiral, and W bosons are preserving a half supersymmetry which is somewhat different. So W boson supercharges has a projection structure which preserves either chiral combinations of the internal and external part of supersymmetry or the antichiral ratio. So it preserves these two. Okay? So the common supercharges preserved by them is these four, okay, which I'll use. So I'm going to study some states preserving this kind of supersymmetries. Okay? And among this, I'll be specifically referring to these two supercharges to define and calculate the index, among which the following linear combination is used by Nekrasov to first define his topological quantum field theory, from which he calculated everything. So the index that I'm going to study takes the following form. It's the kind of Witten index which counts the number of bosonic states minus the number of fermionic states, which annihilate the supercharges that I've chosen. So it takes the form of the trace over the Hilbert space, and it has the -1 to the fermion number insertion. That's the characteristic insertion you have to do to define a Witten index. This kind of term is a regulator. So the Witten index will acquire contribution only from states annihilated by Q and Q dagger. So this B prime value is not appearing in the index. It just regulates out the non-BPS part of the trace. Okay? However, this beta prime or beta will play the role of compactifying the time-like direction into a circle with circumference beta. Okay? And then you can weight all the states by the conserved charge that the BPS particles can carry. There are many kinds of BPS, many kinds of chemical potentials that you require, that you can insert. But the requirement for the Witten index is that all the weight you insert should be commuting with this Q and Q dagger, okay, not to spoil the index properties. So firstly, the chemical potentials you can insert is nothing but the two angular momentums on the SO4, the R4 plane of the space-time. So rotating 1,2 plane and rotating 3,4 plane. Okay? Let us call this chemical potential epsilon 1 and 2. To be more rigorous, to secure the property that the charge you use is commuting with this Q and Q dagger, it has to be twisted a little bit by some internal charges. Okay? So it's twisted with this internal part of this right-handed SU2. Okay? So then these two combinations commute with the supercharges I've chosen. The left-handed part of the internal symmetries can be freely added because it commutes with the supercharges. And then you can weight all the states by their electric charges with the chemical potentials mu I. I mean, the number of these chemical potentials is exactly equal to the number of Coulomb-Webb parameters here. Okay? So this can be calculated from the instanton quantum mechanics as a given instanton number sector. And introducing the fugacity for instanton topological charge, you get the so-called instanton partition function by Nekrasov. Okay? So Nekrasov's original motivation for studying this massive quantity is to eventually work out the following thing. So by this compactification by beta, or the time direction, you eventually be by calculating this index, you'll eventually be calculating certain supersymmetric super-Young mills on R4 times S1, where this can be regarded as a thermal circle. And the Nekrasov's eventual interest for 5-dimensional gauge theories, or its 4-dimensional reduction, was to understand the 4-dimensional n equal to 2 effective action, or its effective prepotential, which has been found out in mid-90s by Seiberg and Witten. He wanted to derive this prepotential in a microscopic way by instanton counting. Okay? So this was an auxiliary quantity that he considered. And after the calculation, if he sends some angular momentum chemical potential to 0, he gave a clever argument that the coefficients of this diverging part in the epsilon 1, epsilon 2, 0 limit is the prepotential that has been predicted by Seiberg and Witten. So that was his purpose. But for us, the main purpose is to study the index information, the BPS states degeneracy information itself, so just 6-dimensional physics. By the way, what will be useful for later purpose is that in this Nekrasov's realization of this Coulomb branch physics, our electrical charge chemical potential has to be naturally identified with the Coulomb-Webb in the Seiberg-Witten theory, and some internal symmetries chemical potential, which I call M, has to be identified with the mass deformation parameter of the maximal super-Young mills, where the mass corresponds to the parameter for the adjoint hypermultiplet if you decompose maximal super-Young mills into 5-dimensional n equal 1 supersymmetry. Okay? So anyway, firstly, I'll try to explain to you briefly how the index looks like, calculated by Nekrasov, looks in the symmetric phase. I'll explain a little bit of physics to you to see that this is giving the describing the 6-dimensional physics of this, the 2-0 theory compactified on R4 times T2, just to give you a brief feeling that it's giving you the correct 6-dimensional physics. But probably the most important reason why I introduced to you this Coulomb phase partition function is that it is also useful intermediate quantity for us to study the conformal phase or symmetric phase of this 6-dimensional 2-0 theory. So the main thing I'll explain to you today as a simple example is how you can use this to study the symmetric phase physics. Please, yes, please.
So the combination
Yes.
is commute
Yeah, it's actually easy to see this because I chose these two charges to define my Witten index, and all these supercharges carry definite J1 and J2 eigenvalues. So let's see. So the Cartan of this right-handed SU2 is nothing but the symmetric combination of this. Okay.
Right.
Right. So maybe minus. I'm a bit confused. Let's see.
Yeah, I think I understand. I mean,
Yeah, the point, yeah, I'm a bit confused with signs and so on, but the point is that these are spin half objects in this R4, so they carry some half integral eigenvalues. An addition of this,
I think
due to this charge, oh yeah, so what happens is that for 1 and 2, the J right-handed angular momentum value is +1 and -1, and this JR eigenvalues for these two supercharges are also -1 and +1 with flip sign. So the addition always gives 0 eigenvalues.
Oh.
Meaning that these two supercharges are commuting with these combinations.
Okay, yeah, I understand. Now that chemical potential epsilon fugacity, epsilon 1, epsilon 2 is 5-dimensional sense that chemical potential, but 4-dimensional sense some background, right? I mean,
yes, yeah. In the 4-dimensional sense, it's just deforming the flat space geometry in a funny way. So unless you have a circle factor, you don't have a chemical potential information. So the effect of chemical potential in the Kaluza-Klein reduced theory down to R4 is abstractly called omega background.
Omega, yes.
But whenever you have a circle uplift, it's nothing but the geometric realization of chemical potential.
I see.
No, please. Yeah. No, but actually, I reduced a few slides, having in mind lots of questions. so please. Yeah.
Give some discussion on, for example, when you have written down this phrase, you said, as you told us, the charges which appear should commute with the particular Q and Q bar
yes.
you chose, right?
Yeah.
Otherwise, it's not a well-defined sort of index.
Right. I mean, yes, exactly. You know, if you are interested in studying general partition functions, you even don't need to insert -1 to the F, and you can insert general chemical potential for arbitrary charges. The point is that if you do so, the measure will not be commuting with any supercharges, and the whole point is that of this big exercise is that if you have some observable commuting with supersymmetry, you can use its power to do some exact calculations, even at strong coupling. I mean, previously there were various reasons we had to calculate a strong coupling limit, even from the quantum mechanics. So the computational power is lost. That's the mere reason. I mean, it's not because this is the most interesting quantity. It's fairly non-trivial, but it's exactly calculable. That's the reason.
And let me ask that G near, G equal to exponential F. How do you, how that Nekrasov, I understand that this formula?
I don't know how Nekrasov understood it. Maybe he derived it, but there's a very easy way of understanding why. So there's a very easier way of understanding this. So roughly speaking, very roughly speaking, this partition function is computing the spectrum of multi-particle states of these quantum BPS particles. Okay. It either counts one particle state, it also counts multi-particle states which are not bound to each other. I mean, effectively, the effect of this chemical potential for angular momentum is somehow providing some potential on R4, on the position moduli space for instantons. So they effectively let them to be localized around the origin of R4. I mean, the fixed points of this rotation. So then what you do is giving some mass proportional to epsilon 1 and epsilon 2, the translation zero modes. Okay? And the index that you're going to get for single particle modes sees in the denominator when epsilon 1 and epsilon 2 goes to 0, the effect of the zero modes. So actually what we'll get for a single particle index is that you have these two factors and you have lots of complicated factors in the numerators. You can understand these two factors in the denominators as the determinant coming from the translation zero modes of the particle, four-dimensional particles. So that if epsilon 1 and epsilon 2 are sent back to 0, you see the expected divergence coming from the translation zero mode, which is massless. Okay? So the fact that you have 1 over epsilon 2 divergence is that you're capturing the spectrum of a single particle index, single particle spectrum. Okay? So if you consider this z, not exponent, log of that, it will get a lot of higher powers of epsilon and epsilon 2. The term which is proportional to this is counting single particle states. The term which is proportional to the square of this is counting the two particle bound states, and so on. There's some infinitely power, I mean, there's increasing inverse power of this as you increase the instanton number. However, roughly speaking, if you take the exponential of, if you express it in terms of exponential of something, the exponent is expressed, can be interpreted as a single particle partition function. And taking the exponential in a more complicated way gives you the multi-particle partition function. So the physics that the log of this quantity is roughly giving the single particle partition function from this index interpretation predicts that the leading divergence should always be 1 over epsilon 1 and epsilon 2 and no higher than that. That's very crucial for getting the single particle. Actually, all the quantities that we will study is the log of this, some kind of log of this partition function, which is actually called platistic log. So this divergence pattern can be easily understood with the index interpretation. Please. Sorry? Yeah. If you reduce it down, if you do the mass deformation, reduce it on a long circle, you get 4-dimensional n equal 2 star system. Yeah. Sometimes it's called 5-dimensional n equal 1 star system here. Yeah. Sorry? Well, I mean, whether the requirement that this should be commuting with this. I mean, it's the requirement that the whole measure commutes with some supersymmetry. It's just to use supersymmetry to do exact calculation. You know, there's much more interesting quantity than this without -1 to the f and more general chemical potentials. It's interesting, but simply uncalculable. Yeah. I mean, with my capability. I mean, it's a cheaper way to getting some non-trivial physics. I mean, the art of this business is to try to define some observables which are calculable, but does not sacrifice some interesting physics. So it's really some kind of art, designing the correct observable. Yeah. Anyway, yeah. Good. Any other questions? Yeah. So the calculation, either the quantum mechanical calculation that you might be interested in, or the 5-dimensional supersymmetric path integral calculation that Nekrasov considered, boils down to this quantum mechanical path integral eventually, using the quantum mechanical Hamiltonian as a measure. Okay? So there is some very advanced technical method that these people in this field employ to calculate this kind of supersymmetric path integrals. I mean, if you're calculating the index, especially in this context, I can simply say that the index is insensitive to the continuous parameters of the theory. Index is acquiring contribution from only BPS states, and from non-BPS states, it acquires always +1 contribution from boson and -1 contribution from its fermionic pair. And it can happen generally in the Hilbert space that if you change the coupling parameters of your theory, the BPS spectrum might be changing. It does happen, but it happens always in the fashion that when a particle, when a state leaves the BPS subspace of the Hilbert space, it always happens in a Bose-Fermi pair. So that index is quite insensitive to this kind of thing because 1 minus 1 is 0. So that index, it gives the property that index is insensitive to the change of the continuous parameters of the theory. So, and also it's independent of the regulator. So by taking advantage of this fact, you tune all these parameters to be as whatever value you want, if that can ease the calculation. For instance, you can take these regulator values to be very small, and then you take some of the parameters I explained to you, something like Fi deformation parameters, to be very large, and so on. And that gives you an effect of changing this generic path integral to a Gaussian path integral, in which the quantum fluctuations are highly suppressed around a set of saddle points. Okay? So in this way, you can employ the easy Gaussian path integral techniques to get the exact expression for the index, using the freedom that you can tune the chemical potential, tune the parameters of the theory to whatever value you want. So the details are quite complicated, but and actually there are many ways of detailed calculation after which you can get the same result. But I'll try to explain it in the way that Nekrasov originally did. So Nekrasov introduced, some ingenious deformations of this theory in his parameter space and adding a few terms which don't affect the path integral if necessary. And he has been able to localize all the quantum fluctuations into a highly suppressed Gaussian fluctuation around the saddle point, except for some zero modes. Okay? So for the zero modes which are not exactly localized after his deformation, were one of the 5 scalar fields in the Coulomb range. And it's complexified with the worldline gauge fields. So apart from the zero mode of this complex scalar, he localized everything down to a Gaussian path integral. So what he did was to calculate the determinants coming from all the small fluctuation fields, whose determinant turns out to be all the factors of Sinches and so on. It's naturally Sinch because it's a natural result of collecting the Kaluza-Klein modes of various degrees along a circle, time circle. And then what has to do is to do the exact integral over this zero mode, which is not localized. Okay? So as a final result, he gets some contour integral for these complex variables. And the contour choice is the whole art of this Nekrasov calculation, which is very tricky depending on problems. But eventually he found out the correct expression for the contour. So the whole path integral just boils down to some reasonably simple contour integrals for k complex variables in the k instanton sector. Okay? I'm just explaining it to you in the context of mass-deformed maximal superharmonious theory, but of course he can do it for all kinds of 4-dimensional n equal 2 supersymmetric theories or 5-dimensional n equal 1s. I'm just explaining a special example of Nekrasov's calculus. Mm-hmm. So let me carefully distinguish what I mean. So this is the diagonal matrix, which is n by n. So this is the field theory web of the UN theory. And this phi, ranging from 1 to 5, they have the same index, but it's the KD0 branes probing the transverse phi directions. So these, decomposing it to 1 to 4 and 5, these 4 and these 1 play somewhat different role because I turned on 5th scalar in the bulk. Okay? So these are all highly localized, and their determinant effect is just erased out after, because I said that this physics is decoupling after introducing this information. This one has a zero mode which has to be exactly integrated over. So it's not having a web, but you have to integrate over it. Yeah. Yeah. It doesn't, because it's the parameters of the theory. It just depends on the electric charge chemical potential, which has a very similar structure to the field theory web itself, but these two are different quantities. This is chemical potential, so it appears. This is the field theory web, so it disappears. So, by the way, I think what I wrote as AI here are all mu I. I was copying different papers of mine, so notations are somewhat inconsistent.
Let me ask. Sorry for interruption. And you combined phi 5 and A tau. A tau is gauge field for the S1 direction.
Yeah, the world line.
World line. And you say that. Let's see. This d phi is complex value, right? Is that right?
Complex value. So it lives on a complex plane.
So you have to choose count hour.
that's the tricky part. So roughly speaking, the following is true. So that's a very difficult technical part, which you have to understand very well if you're really going to do this calculation. Maybe you want to, so that's why you're asking. So in this form, if you define this phi either, these are the, let me say, these are the, oh, sorry. So again, a Klashner notation. This I running from 1 to k are the k eigenvalues of this k by k matrix, different from this SO5 index. I'm so sorry about this inconsistent notation. But these are k eigenvalues. And define the k exponentiated variable like this. The imaginary part of this is naturally periodic. So the contour is taking in the z-planes, all the contour is taking a form of closed contour, some of which can include the poles. And depending on how you choose the contour, the result is changing. As far as I see, Nekrasov hasn't carefully derived his contour prescription. He somehow fitted it by some physical requirements or the result he knows, maybe the requirement to fit the Seiberg-Witten result in its limit or so on. But he could somehow fit the contour and which pole should be included and which pole should be excluded. Roughly speaking, I mean, I can give you a concrete rule. So this measure can be understood as coming from the adjoint hypermultiplet because it contains all the factors of masses. Okay? And the factors not containing the masses are those coming from the 5-dimensional vector multiplet. Okay? So you take all the poles coming from the vector multiplet and take that only inside the unit contour. Okay? And then that gives you the correct result.
Yeah. So could you explain by the very simplest example of the Seiberg-Witten theory, SU2? In that case, mass
is set to infinity, so this factor just disappears. And so all the factors that doesn't contain mass is the pure SUN.
Okay.
Theory. Yeah. And the poles are, there are various poles appearing here and there. And then all the requirement that you take is that take epsilon plus to be very large. It's his prescription anyway. It to be very large. And then some poles will be inside the contour, move into the contour. Some poles will be moving out of the contour. Okay?
I see.
So keep all the poles inside the contour. That's the contour prescription.
Does this pole represent some physical degrees of freedom, like monopole or dione or SU2 case?
Well, in Seiberg-Witten theory, it's not counting states. It's counting an effective action.
But the prepotential contain that information, right?
Well, it requires contribution from instantons, but it's the real instantons interpreted as tunneling, not as BPS states in 5 dimensions.
I see.
In 5 dimension, it's an index for the bound state of instanton particles and W bosons.
So it's not clear the 4-dimensional effective, physical degrees of freedom and this index computation. Is that right? What do you say? Is it? Can you extract the physical information from this index?
Which physical information?
Means as I said, in the 4-dimensional sense, physical degrees of freedom in the dione or.
Well, in the 4-dimensional case, it's not counting these BPS states at all.
Right.
It's calculating lower. Well, of course, from the prepotential, prepotential also contains the information on BPS diodes, but in a somewhat involved way. Exactly in the way Seiberg-Witten does. Once you obtain the prepotential, then that does many jobs.
Yeah.
But the first thing is you calculate the effective action in the Coulomb phase.
But to obtain that, you have to choose counter, right? As you said.
Yes. And the contour is carefully chosen to really give the Seiberg-Witten prepotential. That has been predicted by Seiberg-Witten in an indirect method.
Yeah.
Well, as far as I understand, that's the logic. I don't know whether Nekrasov has a much more deeper reason for choosing this contour, but this is all I could understand.
I see.
Choice contour is not, as far as I can see, not derived from first principle. It's always a subtle issue. Yes, please.
You have phi capital I with capital I going from
1 to
k.
Yes.
But should I interpret that phi as actually phi 5?
Phi 5, and there are k eigenvalues.
K eigenvalues.
Yes.
Thank you.
Yes, it's really inconsistent notation in many ways. It's just.
Thanks.
Thank you. Good. So all the issue is that once you get the correct contour prescription, you identify all the poles inside the contour, the values of phi i's at the poles, and extract out the resids and sum over them. It's quite a technical job again, but let me not make you too worried about that, because the possible contours has been completely classified in Necrosov. I'll just give you the formal result and give you a little bit of interpretation of what it should mean, and just jump to the result. So Necrosov has shown that all the possible poles inside the contour I've shown to you in the integral in the previous slides can be classified completely by what is called the n-colored Young diagrams with K boxes. Let me explain what that is, and give a really short physical interpretation of how we should take that. So if you're doing the K instantons contour integral, just prepare K boxes, okay, and divided that into n parts. I mean, it's a partition of K integer into n parts. Okay? And these are all non-negative integers. Okay? And once you have this division, which each integer that is given, you form a Young diagram with this number of parts. So if K is 1, if K1 is 3, you can have various different kinds of Young diagrams. And you do the same thing for all the other integers. If the integer is 0, there's no Young diagram. And you can form a set of these partitioned Young diagram, which is called the n-colored Young diagram. And the set of these colored Young diagrams is exactly in one-to-one map with the pole that has to be kept. Okay? So let me give you a little bit of more feelings on physically how we should interpret that. So depending on these values, the pole values for the phi i's are all determined. Okay? And note that these eigenvalues of phi are really the positions of instantons, let's say. If the D4 branes are separated with eigenvalue Vi, there are n different D4 branes. There are n different positions in which the K D4 branes can be bound to. Okay? In the Coulomb phase, K different instantons can be bound to n different D4 branes. So this is the meaning of this partition. Okay? Determining which instanton is bound to which D4 branes. Okay? Then, depending on that, for given instanton, the eigenvalue is fixed with referring to the corresponding position for the D4 branes. Okay? And with this division, the further subclassification of each Young diagrams with K1 box, K2 box, and so on, determine the saddle point structures of how this different number of D0 branes on a given D4 brane can be forming some U1 instanton bound states. So this is giving a further dynamical information on how these bound states can be formed. So this can be understood as an abstract pole classification, but it has a little bit of physics for interpretation. Okay? Sorry? Okay, that's a further complicated. Well, in Necrosov calculation, it's very hard to extract this kind of information, apart from the fact that K is divided into n, so that different D0 branes are bound to different D4 branes. In order to get this kind of interpretation, you really have to do a little bit of different kind of localization, which we actually did. I mean, the main purpose was that I was personally not so happy with this contour prescription, so I wanted to localize everything, including this phi zero modes and so on. Then the picture we get is the following. Let me give a very simple explanation for, let's say, U1 instanton with K equals to 2. It corresponds to K1 equal to 2 or something. So the prescription predicts that there are some kinds of 2 instanton bound states at the points. And if you investigate the U1 2 instanton bound states, the U1 instanton has position 0 modes for each instanton. And if you decompose it into a center of mass and relative position, it gets a Z2 factor because instantons are identical particles. Okay? So the relative instanton moduli space is this, okay? Which is again singular. If you introduce a slight regularization given by an Fi term, it again becomes the Eguchi-Hansen space, okay? Which resolves this singularity. So at the center of the Eguchi-Hansen space, you get roughly the structure of S4 times R2. Okay? And the instantons under the omega background is required to be localizing onto the tip of this all this R4 before all this deformation. But after this deformation, the instantons can be localized into either north pole or south pole of it. So that's exactly the interpretation of these 2 Young diagrams. And if you do it for more complicated moduli spaces, you get this different set of saddle points. Okay? So it really has to do with the structure of the instanton moduli space and how you resolve it, the singularity. I mean, this is all about this Young diagram.
Sorry, Sok. Does this Young diagram represent the representation of the SUN or something?
It really, well, it really has to, SUN.
I mean, you could say UN gauge theory, right? UN or SUN now. I mean,
More has to do with K, I would say, but, you know, of UK eigenvalues into n different parts and so on.
what I want to ask is that, you know, in the anti-fundamental representation, you know, how can I say? K, you know, the limit bound there, right? In the lower wise bound.
What is bound to what?
Bound meaning if you k equal to 3 case, if you put the 4 box in the lower direction, then that should be what is that right?
Or, you know, it doesn't correspond to any allowed fixed points. I mean, if k equals to 3, you have to consider the U13 instanton moduli space on the where the relative position is now subject to the modding out by the permutation group. So it's again relative moduli spaces again given by some cone geometry with singularity. I mean, you have to resolve this again, and the fixed points of the resolution only has, I mean, 3 fixed points. So it's nothing corresponding to anything else than this. It's some mathematical way of quickly classifying all the.
I want to understand physics by this, you know,
Well,
classification of the bound set, right? Some mathematically classified by Young diagram, right?
Some
I want to understand
the
that physics.
mathematical people should know that. I've only checked it for U2 case. U3 case should be possible, but yeah, I've only checked for the U2 case where concrete metric is known. Yeah. For other cases like UN, single instanton, you know, it's just given by 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and so on. And these n fixed points could be found here because the moduli space metric is known, even after non-commutative deformation. But if I don't have concrete metric, I mean, my concrete thinking just stops there. So abstract math, I'm not very sure about. Well, anyway. Sorry, say again, please. Uh-huh. Partition of what? Permutation of instance. It could have something to do with that. I never thought about that, but it could be. It could be. You know, because this orbifold really has to do with the permutation of identical instantons. It naturally could have to do with the representation of that. Yeah, that I strongly believe that should be the way of thinking about it properly. Yeah, I think so. I think so. But then it should be symmetric and anti-symmetric, and I don't know what anti-symmetric means. So,
symmetry is kind of obvious.
Yeah. It may or may not mean. So I'm not really sure. Yeah, because there's no real big distinction between this and that. I mean, the distinction between this and that fixed point is just epsilon 2 and epsilon 2 are exchanged. So it has to do with the exchange of two R2 planes. So it's, yeah. Anyway, well, you can just take it as a mathematical classification of poles in the previous formula and just collect the resids. You get another massive formula like this. I mean, all referring to the information about the colored Young diagram you got. So maybe I should skip explaining that. I have almost no physics to say about that. There's some detailed rules. You know, it's a summation of all possible Young diagrams, and given Young diagram, you get a formula for all the resids, which refers to each of the product refers to each box appearing in this colored Young diagram. And whenever you have a fixed box, something like, and whenever you have a fixed box in a large Young diagram, box is labeled by S, this H denotes the distance between the Young diagram, the box you have, to the right end of the Young diagram. So this is some horizontal distance to the right edge of Young diagram. V denotes the vertical distance to the bottom of the Young diagram. So there's a very concrete prescription for this resid. I mean, after you evaluate the contour integral carefully, it's a massive but very concrete expression once you get used to these calculations. So you get a definite index expression for the bound states of W bosons and D0 branes at K instanton sector. So this is the concrete expression we get. So once you have this kind of expression, before moving on to a more complicated and probably more interesting setting, I may be able to explain to you a little bit of physics on how it successfully reproduces the expected physics in the Coulomb phase for the 6-dimensional theory. I mean, the question is whether if you sum over all the instant numbers with chemical potentials inserted for it, whether the Kaluza-Klein mode physics is correctly coming out from this instanton sum, which is highly unclear from the solitonic particles point of view. Okay? So let me try to explain the simplest physics one expects from M5 branes and M theory, and just give an illustration that it really works from the instanton calculus. So very fundamental questions ever since the emergence of M theory in the 1995 is that whether the D0 branes, either with or without the presence of M5 branes, is forming the correct Kaluza-Klein bound states to account for the expected Kaluza-Klein states of the higher dimensional theory. So for instance, in the 11-dimensional context, the type 2A D0 brane bound states, appropriate number of them should be formed at each instanton number level to account for the Kaluza-Klein modes for the 11-dimensional supergravity fields. So since you have a given set of 11-dimensional supergravity supermultiplet and decomposing it into each Kaluza-Klein mode, you have exactly the same massive field content coming out from the 11-dimensional supergravity. So the prediction from the M theory viewpoint is that given number of D0 branes, there should be basically unique bound states. I mean, meaning the unique massive supermultiplet given for each D0 brane number. Okay? You can do the same for the U1 6-dimensional theory with circle compactification, because the theory you have in 6-dimensional is just one single tensor multiplet. You decompose it into Kaluza-Klein towers into 5D. At each Kaluza-Klein momentum, you have only one massive tensor multiplet. Okay? So the prediction is whether instanton is reproducing that. Okay? So the bulk problem in carefully in the 1997 by Pilchini and also by Setiston, and later by Nekrasov, Moore, Kshatashvili. It was a very complicated problem. Somehow, for some technical reason, in the presence of D4 branes or M5 branes, this problem becomes much more simple. I mean, the Nekrasov partition function is doing this job.
Sorry, just to understand.
I mean, especially the many young people, including myself.
Yeah.
So the very important thing is that from the geometric viewpoint of 11 dimension, you start from one supermultiplet Kaluza-Klein decomposed. So at each Kaluza-Klein momentum, you should have a unique bound state essentially.
Yeah.
But the quantum issue in the lower dimensional viewpoint is that you consider multi-particle physics of D0 branes, and they should form exactly one threshold bound state. That is the quantum question.
Right.
Actually, I forgot. I mean, I actually didn't know when I was a student, but I was reminded by my seniors in Korea. Kept emphasizing. Maybe Pilchin was not so happy that this important problem is forgotten after he solved it. So, actually, this is his phrasing, almost. So, I just got reminded of the importance of this problem when I got to my problem in 6 dimensions. So, I also keep emphasizing this. But anyway, it's a requirement for the consistency of M theory. So anyway, if you start from the U1 Nekrasov partition function, which is the sum of refs of complicated sorts that we got, it has a magical rewriting which is given in the following form. So it's given by what's so-called platistic or multi-particle expression of the following simple expression. This can be obtained by some ingenious techniques. I mean, not just by Nekrasov partition function, but rewriting of it using some topological string techniques. But this funny exponential is given in the following form, and it physically simply does the following job. So the small function of f in terms of fugacity, as a function of fugacity, is what is called a single particle partition function. Okay? And the platistic exponential given in the following form is nothing but giving you the multi-particle version of that once the single particle partition function is known, where all the multi-particles here are the non-interacting identical particles. So this is actually a formula that you can find in the statistical mechanics textbook, disguised in a different form. So the fact that the U1 instanton partition function can be written in this way is signaling that this is the single particle partition function for the pure U1 instanton. I mean, bound states of momentum only. Okay? So it takes the following form. The prefactor is depending on lots of factors, and it takes the geometric series form of Q. So if you expand this geometric series, you get Q plus Q squared plus QQ, blah, blah, blah. So this is giving the desired structure. It says that the spectrum structure is exactly the same no matter what the instanton number is. So it gives the same spectrum for Q square, same spectrum for Q cube, and so on. So this coefficient function should be the index coming from a single massive tensor multiplet obtained from reduction from 6D. And indeed, you can show that this is the index for the 5-dimensional massive tensor multiplet, which is showing that this 5-dimensional calculation is at work, at least in this very simple example. Of course, it's abelian theory, so nobody will be interested in, but it illustrates that things are working very correctly in this kind of framework. Of course, you can do the same thing with non-abelian case with electric charges put in. And there are some non-trivial results also in this case that the instanton sums are organizing itself into the correct way so that the 6-dimensional or the 2-dimensional world sheet physics of the self-dual string is coming out correctly. Well, this is just the result, and let me just pass on this subject by just saying that there are some more works done for the higher gauge groups and more complicated chart concepts, but it just becomes more complicated.
The previous slide, could you go back to previous slide? Excuse me. And Q, this Q counts the number of instanton, right?
Yeah.
The coefficient is degeneracy like that.
What was that?
Degeneracy, kind of degeneracy. Is that right?
What is degeneracy? Oh yeah, the index calculated over the states with definite Kaluza-Klein momentum. Okay? And the consistency with 6-dimensional theory that we know, that this should be the index for the single massive tensor multiplet, reduced down from massless 6-dimensional tensor multiplet.
Okay.
So this is the spin content of the 5-dimensional massive tensor multiplet. Okay? So if you, tensor multiplet, and if you calculate an index over the 5-dimensional massive tensor, again having some 4 translation 0 modes on R4, you exactly get the result calculated from the instanton calculus. This is a independent calculus carried out from 5-dimensional tensor multiplet, and this is what has been done by Nekrasov instanton calculus. The coefficient function exactly agrees with this.
I see. And what's the meaning of, for example, one? In the leading in the partial function, leading part.
This one.
One.
Oh yeah, I just expand out this quantity.
Is there a physical meaning of that part?
One, just nothing.
Nothing?
Just a ground state.
Always comes one.
Yeah. I mean, it's the sector with no momentum. It's just for the vacuum.
Okay. A unique vacuum, you mean? Is that right?
Yeah.
Okay.
I mean, it's the U1 theory and just. I mean, the instanton part. I mean, the ground state for the instanton part of the partition function with no instanton charge at all. There's nothing, so it's one.
Okay.
Yeah. Good. So how much time do I have right now? I mean, in the strict sense.
You've had quite a few questions, so maybe you can take 10 minutes or 15 minutes extra as you feel, and there's also time in the afternoon.
Maybe I can postpone something to discussion.
Yes.
Then what's the? Yeah, then 10 or 15 minutes.
Yes.
Yes. Okay, then I'll postpone some auxiliary subjects till the afternoon if people want. Okay, so I was preparing a couple of slides, which was about the recent developments by these collaborators, Rafa and company, about the recasting of this Nekrasov partition function. Because as I explained to you before, the Nekrasov partition function is, in some sense, really difficult quantity in that it obstructs the really expected structure of the 6-dimensional Kaluza-Klein mode structure. So they were using some ingenious reinterpretation of Nekrasov partition function to exactly sum over all the instanton series in the Nekrasov partition function and have an alternative formula for that, after which the Kaluza-Klein state structure of the Coulomb branch physics becomes really clear. Just a few slides, and I'll explain these 3 slides later if anybody's interested in it. Okay. So let me move on to the last subject, which, for the continuity of the subject, next lecture, which I think is more important. So somehow we got this Nekrasov partition function in the Coulomb phase. And it turns out that it's extremely useful also to study the symmetric phase physics. both of 5-dimensional super Young mills and also the related 6-dimensional conformal field theory. Okay? So it's much more interesting physics. But also, always the problem is that the instanton dynamics becomes extremely subtle when you study it in the symmetric phase. The most subtle aspect is that it has a scale modulus, especially the large scale instanton. Its physical interpretation is not really clearly understood, apart from the guess that it will have to do with some infrared behavior of the 6-dimensional theory. So what we're going to do is the following. So first I start from the calculation and observation. So during the course of quantum mechanical path integral, what plays really important role is the chemical potential for the electric charge. You know, the Coulomb wave, after all, just decoupled, I mean, just doesn't appear in the index. And if you have a look at this detailed localization calculation, the non-zero value of the Coulomb wave really doesn't play any role anywhere, supposing that you turn on this chemical potential. So even in the case where Coulomb waves are turned off in the symmetric phase, having the UN gauge symmetry, suppose that you are introducing these chemical potentials in the maximal Cartan, labeling the non-abelian gauge charges of the W boson states, all the calculation can be carried out, even without the subtleties of small instantons and so on. Because if these chemical potentials are so turned on, it provides some potentials on the instanton moduli space, so it lets the instantons to shrink. Okay? So this kind of temporary introduction of electric charge chemical potential is in some sense providing the infrared regulator of the problem. It makes all the infrared divergence coming from the large instantons moduli space integral, all absent. So you can do some calculation with this infrared regulator. The result you get is exactly the same as the necklace of partition function, even in the symmetric phase where all the Coulomb waves are turned off. It's natural because it doesn't depend on it. The only remaining thing is how to use it or how to properly interpret it. It's somewhat usual in all systems which has infrared divergences. You have to cook up a careful observable which is free from this infrared divergence issue. So you got the necklace of partition function. The issue is what you're going to do with this regulator. And cook up some finite observables.
Sorry for interruption. 4-dimensional, you say that this index contains prepotential in 4-dimensional sense,
yeah,
right?
In Coulomb phase, yes.
In that potential, is computed in the Coulomb branch, right?
Yes, yes.
So in that sense, prepotential is always Coulomb branch in the 4-dimensional sense. Yeah. But you say that it is 5-dimensional index can be computed with, symmetric phase.
So the interpretation, this cyber-Witten interpretation, as far as I know, completely breaks down the symmetric phase.
So what that
I'm going to give a totally different interpretation or usage of the same quantity in a totally different context.
So what's the meaning then in 4-dimensional sense in this symmetric phase index?
I don't know. Maybe it doesn't have any meaning.
I see.
I don't know. I don't know.
I see.
Yeah. I just realized that this result makes sense regarding this as an infrared regulator. Then I considered what kind of interpretation I can give in terms of D0, 6-dimensional physics. I found one interpretation, but I don't think that's all. There may be more interpretation about the same quantity, which I don't know. So I'll just give you one interpretation on how to take this kind of quantity. How to take this necklace of partition function in the symmetric phase with this regulator. Oh. I just have one interpretation I can give. Let me just get to that. Okay. There are many things I don't know about it, actually. Yeah. So to really give my interpretation on how to use that in the symmetric phase, you have to get to the DLCQM5 physics again. So let me talk about it in more detail. So it, practically speaking, it's obtained by compactifying the 6-dimensional systems on a finite light-like circle, like giving some finite light-like momentum. And it physically corresponds to describing a system at a very special scaling limit of doing the spatial compactification, setting the spatial radius to be 0, and doing the infinite boost, and describing the system there. Okay? Anyway, if you do this light-like compactification, this is the full superconformal symmetry of the 6-dimensional system, and the surviving subgroup of the symmetry in the DLCQ description of the null relativity quantum mechanics of instantons is only seeing a subgroup of this symmetry commuting with this fixed value of light-like momentum. Okay? So that symmetry group is fairly non-trivial. Firstly, taking a look into the conformal group in 6 dimension, this SO6,2, containing the 6-dimensional Lorentz group, so the translation, conformal transformation, and the dilatation, CL transformation. And those combinations which commute with this P minus can be written down as follows. This contains the Hamiltonian, Lycon Hamiltonian, spatial translation, rotation, Galilean boost, and the time spatial conformal transformation. And finally, a funny combination of dilatation and the boost along this compactified circle direction, which I chose to be 5. Okay? So if you do the dilatation, this radius changes. I mean, if you compactify it on a small circle, this radius, space-like radius changes by dilatation. But if you boost along the circle direction, it also changes. So if you make a careful combination, it commutes with the given radius of the compactification. It just commutes with this. So we call this the non-relativistic dilatation operator, realized manifestly in the instant of quantum mechanics. So actually, the instant of quantum mechanics is a superconformal quantum mechanics, seeing some non-trivial conformal part of the 6-dimensional symmetry. Okay? So geometry comes from the fact that the target space metric of the instant modulus of the sigma model takes the form of a cone geometry. Dilatation transformation in the non-relativistic form just scales all the coordinates homogeneously around the tip. So especially important part is the SL2R subgroup, which is common in all the superconformal quantum mechanics, consisting of the Hamiltonian, non-relativistic dilatation operator, and the special conformal transformation. Okay? You can form this in the following basis for convenience to see the familiar SL2R algebra. You can also see that 24 out of 32 supersymmetries commute with this, actually quite a lot. So you can use these 24 supersymmetries to define some supersymmetric observables in superconformal quantum mechanics. Okay? So let me try to explain to you what kind of superconformal index, what kind of index referring to superconformal, non-relativistic superconformal symmetry you can define in this kind of quantum mechanical system. What is called the non-relativistic superconformal index has been also explored by certain groups of people. It's taking really the same form, but it refers to one supercharge in the Poincare supersymmetry and one supercharge coming from the conformal supersymmetry, and try to consider this kind of bound, which is a characteristic one which appears in all the kind of superconformal algebra. So commutation relation of this 1Q and 1S supercharges is what giving you one element in the SL2R algebra, which is a combination of this, and in this kind of problem you regard it as a Hamiltonian. Okay? And that is given by and that is linearly combined with some combinations of R charges and the space-time rotation symmetries. So you can define an index which saturates the right-hand bound, which counts the BPS states having the right-hand side to be 0. So its energies are all given by some combinations of R charges. So following the very similar logic, you can define this kind of non-relativistic superconformal index. The only difference is that you don't have electric charge chemical potentials because you're in the symmetric phase. So this kind of state index is counting the spectrum of gauge invariant states in your system, or equivalently via the operator states map in any conformal field theories, you're counting some spectrums of gauge invariant local operators, okay, in this framework. So you do the path integral for this kind of object, starting from the superconformal mechanics. And basically what you do is the same calculation. You find that exactly you get the same Nekrasov calculation that I explained to you, but with this regulator chemical potential playing the role of the chemical potential for color charge integrated over at the final stage, because you want to investigate the gauge invariant states. Okay? So if you integrate over this is giving you a perfectly finite, well-defined states, counting some gauge invariant states of non-relativistic quantum mechanics. So this is what I have to do with the regulator I introduced in the Coulomb phase. And this turns out to be, this quantity is exactly the Nekrasov partition function, and it turns out to naturally appear during the calculation as an intermediate quantity. So I'm explaining this because this is a prototype example of the appearance of Nekrasov partition function, which even appears for the symmetric phase physics. Okay?
Excuse me, what's the alpha I?
Alpha I is the imaginary rotated chemical potentials, and which is regarded as an angle value.
So holonomy like that?
Holonomy along the circle for the gauge.
And that 2 sine blah blah is that coming from?
Haar measure. You insert the Haar measure and do the integral. This is the way you project things down to the gauge invariant states. You
So
just extract out the gauge singlets.
I see. I mean, a little bit technical, but how do you compute that? I mean, gauge theory, right? You compute it, so you have to gauge fix.
Yeah, I mean, essentially what you do is doing exactly the same calculation, but having in mind that your Hamiltonian is not H, but H plus K, L naught. That all the difference coming from this all disappears if you do the localization calculations, giving you the same measure. The difference is that after you get the same measure, you have to integrate over it.
I mean, that kind of measure usually or coming from Fadifov determinant, no,
Yes, yes.
by the Coulomb. I mean,
Yeah, I think you can get it by hand, but this part we just did. I think you can do it by more honest calculation. This part we just did it by hand because the physics we have to get became very clear at the stage we obtained this kind of thing. Yeah, yeah. It should be the Faddeev-Popov measure for some gauge. Yeah.
I see.
But at this stage we worked somewhat combinatorically. We obtain some states, we operate local operators charged on the gauge transformation, then we project out to singlet by hand. Up to this part, we calculate by quantum mechanical path integral.
So quantum, yeah.
Inserting this as a Hamiltonian. But you get the same result as Nekrasov.
Okay.
This part we impose combinatorically, just by hand, from the physics we want to study. So anyway, I'd just like to emphasize that this gives you the really correct physics starting from the Nekrasov partition function. For instance, this start from the Nekrasov partition function for UN theory at single instanton level, and do the Haar measure and the gauge singlet projection, you get this kind of complicated quantity. Okay? And this is really giving you the correct physics. It is consistent with some cohomology counting of this DLCQ M5 brain theory in the early days by Seiberg and collaborators. And also in the larger limit, it's precisely reproducing the gravity dual index on ADS7 times S4 if you do the DLCQ and ADS7 as well. So this is the gravity spectrum on the DLCQ, and the larger n index that can be obtained from it is exactly agreeing with that. So it's an illustration. I mean, it's not something big, I think, but apart from the agreement with ADS7 gravity, but it's giving you a concrete feeling that you can use this Nekrasov partition function for more non-trivial problems in symmetric phase. Okay? That's the message I wanted to give, because what I'm going to talk tomorrow is a much more complicated example of this sort. Okay? The Nekrasov partition function on flat space, R4 or R4 times S1, it turned out to appear in many places as an intermediate in gradient. Let's say if you want to calculate some curved space partition function of various gauge theories. A typical example is the four-sphere partition function of gauge theories calculated by Peston. Okay, so it's a partition function of a compact manifold, so there's no notion of Coulomb phase. But if you do the path integral, the intermediate saddle points turns out to be an expectation value of scalar, which is very reminiscent formally of the Coulomb wave. And with this fixed value of the chemical potential, the measure turns out to be a copy of Nekrasov partition function of flat space. And with that in the measure, you have to do something, integrating over the saddle point value. Very similar to the small version that I've shown to you. It appears here. Nekrasov partition function appears here in a more complicated way. This kind of fashion will be repeated in different kinds of partition function in five-dimensional Yang-Mills, where in that case, R4 times S1 partition function will be playing more important roles. So this will be the subject of my next lecture tomorrow. Yeah. Yes. Yeah, that was because basically I was studying the physics of M5 planes on flat space. Here you are studying the physics of curved space, so it's S4. So if you carefully localize the partition on S4, you have a north pole and a south pole, and all the quadratic fluctuation determinants can be regarded as getting contribution from local alpha on the north pole and local alpha on the south pole. The determinant calculation factorizes, and each factorized part becomes one of the two. Yeah.
One part is instant contribution, and the other part is anti-instant, is that right?
It has an inverse power of
the other
yes.
Complex conjugate, is that right?
Yes. That's the reason why I had mod square.
I see.
Regarding Q as being complexified.
And the previous slide, you consider some gravity dual, right, of this.
Yes.
And what's the counterpart of the instanton on the gravity side?
Well, it's just, gravity. Look, ADS7 also has radial direction and coordinates for R5 times 1. And you exactly do the DLCQ for this. And instanton corresponds to light-like momentum for particles on ADS7 along x minus direction. Just the same thing. Yeah.
So first the corresponding to the bound state, for example.
Sorry?
Bound state. In the you compute in the field theory side. There is
Yeah,
a
yeah, I'm
bound state,
computing
right?
bounds, non-trivial bound state
Bound
like
state,
this
right?
here, but in gravity, you're all calculating free graviton particles.
Hmm.
So the viewpoint is very different because it's ADS-CFT.
So you are saying that that bound states cannot be seen or
It's just free particles.
just
Just like the
Ah,
abelian instanton calculation being recasting the free six-dimensional tensor multiplex Kaluza-Klein spectrum.
uh-huh.
Whether it's free or not depends on your viewpoint.
I see. So I see. So I mean, so you computed some instant index, right? And you said that some parts corresponding to this light, I mean, Karuskal mode of the light cone direction. The other part is how do you divide or do you understand what my question?
No,
My
no,
question is, you computed the instant index, and that instanton corresponding to some Karuskal mode of light-like Karuskal mode, and you say that some other part is tensor muscle multiplet or something. You said, is that right? I mean, gravity mode, just gravity mode in the ADS.
Okay, so this is the gravity multiplet. So you can form a single particle gravity index with single momentum.
Okay,
At the
yeah.
level of single momentum, single particle index just gives the full index. Because with single momentum, you cannot form multi-particles with non-zero.
Oh,
So at the level here, you form the single particle, calculate the single particle index, and it agrees with this. But from the higher instanton sector, higher Kaluza-Klein momentum sector, you have to calculate the multi-graviton particle index and compare with the instanton calculus.
Okay, yeah.
Yeah. So yeah, that's it for.